Hi, everyone. I'll start talking about the objective of the logs QC and the typical workflow of a rock physics project. Then I'm going to show you some examples of measurement issues and what do we have to have in mind before starting QCing the log data. Then I'll move to the software, where I'm going to show you how to do a single well and multi-well QC analysis and some basic conditioning steps. And finally, I will end the presentation with a conclusion. Quantitative interpretation is based on rock physics analysis. This analysis should be a fundamental part in all projects because it will allow us to understand the relationship between the petrophysical properties, or the geology, and the seismic response. Now, we can perform a solid, robust rock physics analysis if the log data aren't good enough. If this is the case, then we need to create or design a workflow to improve the quality of the data and to predict any key missing logs. Once we have a suite of logs already QC and conditioned, we should take the data available to construct some simple models to explore the range of different seismic responses and to use them to improve the way we interpret seismic data, and hopefully to also fast-track the process to find leads and new prospects. Something that is very important to mention at this point is that we need to set the right expectations, meaning that the result of our analysis will depend on the quality of the input data. Remember, rubbish in equals rubbish out. The first step in any workflow is to evaluate the quality, availability, and consistency of the data we would like to use. Make sure that you have as much data as possible. Ensure that when you're looking at the data, you have at hand all the corresponding QC logs, such as caliper, density difference or D-row, Poisson ratio, etc. If you're working with petrophysical data done by someone else, make sure to look at the interval consistency of those data. Often you will find the petrophysical analysis done by different people at different time. The parameters you get in the analysis won't be different across all the wells. So there's going to be inconsistency in the data. Look for intra-well consistency of logs. In this case, we need to have in mind if there are consistencies in the changes in the log responses in each of the different geological formations. Are there specific changes at specific intervals that can impact the quality of your data? Also, look at the interwell consistency of the logs. Ensure that you're using any offset well data available. For example, if in your key well you don't have measured data or you have some missing logs, you can use offset well data to predict the logs, as long as the geology is similar, of course. And lastly, look at the interformation of log responses. Maybe you're using trends for each individual formation, but it turns out that the formations all have the same similar trend. This will simplify your workflow and reduce time. Let's take a quick look at a typical quantitative interpretation workflow. The first step is to QC the log data because together with the petrophysics, you can design a conditioning workflow to ensure that your logs are of the highest quality. Once we have a full set of conditioning logs, we can move forward to a more detailed seismic modeling studies, looking at specific geological scenarios and potentially modeling seismic responses at prospect location. So how can we model these different scenarios? Well, we can combine our log data together with rock physics models to come up with cases for example, different fluids, lithologies, pressure, and for each cases we will have a different synthetic response that then we can compare with our seismic. And this will help us to understand what the seismic is telling us. Before showing you some examples of measurement issues and how to identify them in the logs, I would like to talk a little bit about the borehole environment. Wireline logging has the purpose to give accurate and representative data on the physical property of the rock formations and fluids encountered in a well. The tools used to take this reading have to cope with extremely tough conditions downhole, particularly high temperatures and pressure, and the physical constraints imposed by the physics of the measurements and the borehole geometry. It should also be remembered that we're interested in the properties of the rocks in undisturbed conditions, and the act of drilling the borehole is the single most disturbing thing that we can do to a formation. This is why we need to assess the impact of the borehole environment on the log measurements we take. So, let's take a look at some measurement issues and how we can identify them at the logs. First, let's start breakouts. Borehole breakouts are a stress-induced enlargement of the wellbore. So when the wellbore is drilled, stresses become concentrated in the wellbore wall, and the result is that pieces of the borehole wall will fall off. So for example, in here, I have a well panel. And I hope you can see where my mouse, the location of my mouse is. I'm indicating the caliper track. And this is a decal, or what we call is a caliper minus bit size curve. And it's highlighting in red where the washouts are, according to the caliper. And then let's take a look at the density, which is the last track in the well panel. And the red arrows are indicating where the density drops because of the washout. Okay. Something that we have to think about is the interpretation of our density, of our logs, in this case, the density. Because if my lithology indicates that I have coal, then probably we'll have to assess if this density response is low because of the coal or the washout. Another effect that we need to look for is a whirl, the whirling motion. A whirling motion of the drill is caused by interaction between the drill string and the borehole wall. It can result in spiral holes. There are regular high-frequency oscillation of the borehole wall, and that can have an impact of multiple logging times, okay? So how can we identify this at the well? Again, we have an example in here, and let's take a look at the caliper track, the density, and also the BP track. All these logs show a small variability in a particular section, okay? And these are indication of this whirly motion. If you have something like that with your own data, probably you will have to remove it, okay? And then model the data to replace that section. Now, mud filtrate invasion. The in situ formation fluids may be replaced by mud filtrate during the drilling process. The depth of this invasion is controlled by the permeability of the formation. In permeable formations, a mud cave develops more rapidly and prevents further invasion. Now, in the example that I have in this slide, we have an oil-bearing well which was drilled with a water-based mud. So if you take a look at the density, the measured one, which is the log in black, the response in the oil leg is pretty much similar than the response in the deeper section where when we have the water leg, okay? So that means that in this case, the density in the oil section of the well is actually measuring the water-based mud filtrate. It's not measuring the in situ fluid, okay? So what we need to do, we need to correct the density log. In this case, we use a mass balance approach, which assumes that the porosity was core calibrated, okay? So basically what we're doing is we're removing or taking out the density of the mud filtrate, and then we are replacing that with the density of the oil, okay, that we have in situ. Another issue that we can see sometimes is cycle skipping. This is the occurrence of a failure in the thresholding to detect the first cycle of the wave's first arrival. Triggering may then occur at a second or even a third cycle, and this causes a marked and sudden shift to higher sonic values, followed by a shift back again to the correct values. So the way that we can identify this is, again, let's take a look at the sonic track that I have here. If you see this continuous spike like we have in the shallow section, and then again in the deeper section, these are indications of side skipping. Okay. Another issue that we need to have in mind when we're doing any sort of a well-based workflow is anisotropy. Most of the time, when we are doing any kind of modeling, we always assume anisotropy because it's easier. Sometimes actually we don't have enough data to do a proper anisotropy analysis. But if you're dealing with multiple wells across a variety of different inclination angles, there are some simple QCs that you should do. You can start first by cross-plotting density as a function of BP and color the data by inclination angle. Since density doesn't get affected by anisotropy in the same way as velocities, we can expect density to remain fairly comparable as we change inclination. However, velocities, especially in the shells, will increase depending on the inclination. Then we can cross-plot BP as a function of inclination, but always accounting for the effect of compassion. To try to estimate the magnitude of the anisotropy parameters, like epsilon, gamma, and delta, and then we can use those to verticalize the logs. So in this example here, the curve in red, they are my Thomson parameters curve, epsilon, gamma, and delta. And we use those to verticalize the VP log. So in this track, in the velocity track, we have in black the measured VP log, and in red, the anisotropy corrected VP log. And as you can see, the anisotropy corrected is showing in the deeper section lower values than the measured VP. Now, when we want to start a project, and obviously we need to start QCing the logs, there are several factors that we also need to take into account. The first one is data loading. Data will come in a variety of different formats, like the list, last. There are multiple versions of last files, and some files format don't support certain data types. For example, last files don't support multidimensional logs. We also need to consider the data source. Were the data exported from a data store or a database? Were the data exported correctly? Are we looking at the original data or an edited version of it? And if it's an edited version of it, how was the editing done? Something that also very important is the data sample. Is the sample consistent across all the logs and wells? Sometimes we see lots of vertical variability in, for example, the VP and density logs, but not so much in the VS logs. And this will indicate that the VS log was sampled with a different rate than the other logs. If this is the case, you will need to resample your logs again. And then consider always the data coverage. Which tool has been run in the borehole and over which depth? Make sure that you have all the measured data available, and ensure that you're using the best quality data if there are multiple repeated runs over the same depth. Another factor is log verification. This is very important to make sure that the data were loaded correctly. QC the logs against any available image log if they're available. Also, take notes on any remarks, particularly if there are any issue with equipment and tools. And if you have the time, try to check the well reports as well for any comments during the position. Use logs like caliper, bit size, and density difference to QC the condition of the borehole, and look at the tension log for overpull and tool sticking. Now, log edits and shift. Once we load it and verify the well data, we need to move on to the editing step, where we should remove the data above and below casing, and also remove the data that were affected by tool failure and washout. It is important to check if all the logs are on depth with this log. If not, the logs will need to be depth shifted reference to a baseline, and make sure that you select the right baseline log. This could be the density, it could be the resistivity. And always be aware of any tool sticking issues. Here, I'm showing an example where we can observe in green the tension log in the first track. And we can see some indication of tool sticking. Where that tool sticking is happening on the different petrophysical logs depends on the position on the borehole. So for example, in here, we can see some effect of tool sticking on gamma ray, but at different depth, we can see the effect in the density and also the neutral porosity logs. We may have multiple runs of logs, and we may have logs acquire different techniques. So we want to make sure that we do a detailed QC and review all those data that are available. If there are ways for image data, ask to your petrophysicist to look at them and QC them alongside the logs that have been provided to you. Always ensure that you're receiving the best quality data available given the data that has been acquired. And of course, we have a log spline. If there are more than one run, then we need to start splicing multiple logs together to create a composite log. This is typically one of the first deliverables that we would like to receive from the petrophysicist. And we need to make sure that all the basic checks has been done. For instance, that the logs has been depth shifted accordingly, obviously if was necessary, and it has to be done before splicing. Make sure that all the curves you have are appropriately labeled, and those labels and mnemonics are consistent across the dataset. So now I'm going to move on to the software to show you how to do this QC analysis. All right, in this opportunity, I'm going to use a well from the west of Shetland to show you how to do the single well QC analysis. So what we can observe here is all the logs that I have available for this well, and this is raw data, okay, without any conditioning. So we have gamma ray. In the caliper trap in red, we have the caliper minus bit size. Then we have the lithology. We have porosity with fluids. And then we have a raw VP, VS, and density. We also have the density difference, or D raw, in red. And from the measured VP, VS, and density, we also calculated some Poisson ratio and acoustic impedance. Now, let's take a look at the red curve. So you can see here, for example, in the caliper, in the shallower section, this caliper minus bit size is showing some washouts, okay? And if we take a look at the density, where we see the washouts, the density has very low values, okay? Same happens in the middle section between 1700 and 1900 meters MD. The caliper is showing some washouts, and the density is also showing some low values. But you may say, well, if you look at the scale of the density, these values look okay. But if we look at the lithology, according to the V-shell, in this case, or the petrophysics, in theory, we have a very clean shell section. So at deep depth and clean shell, we are not expecting to have these kind of values for the density. Another comment about the density that I would like to make is in the shallow section, yes, caliper is indicating washout. But if I zoom in, we can observe that according to the petrophysics, I also have cold. So we have to have this in mind if we would like to condition in the density, okay? So if these values are real, because of the cold, we should leave them as they are. If they're a consequences of the washout, then we have to remove them and condition later on, okay? Now, let's take a look at the VS log. If you have like a first visual QC, again, you will say, this looks okay, it has reasonable values. I don't have time, let's move on. But the best way to QC the VS log is actually calculating the Poisson ratio, which is the one that we have in here in the Poisson ratio track. In the shallower section, my Poisson ratio is showing very negative values, okay, which of course are not realistic. And in the deep section, my Poisson ratio is showing a higher values. It's true that these higher values are within the physical bounds that we're expecting for Poisson ratio, but again, let's look at the petrophysics. We have sand with a porosity of around 10–15%. So for this kind of lithology, we should have a Poisson ratio between 0.1 and 0.3, depending on the fluids. No Poisson ratio higher than 0.3. So this is again telling us that we have to condition the VS log. Now, let's take a look at the acoustic impedance. There are some spikes in the acoustic impedance, and I'm going to zoom in to take a better look at it. You can see there are several spikes or ticks or increases of acoustic impedance, okay, across the entire well. How do we know if these spikes or changes in acoustic impedance are real? We need to take a look at the VP and the density log. If we have that spike in both logs, probably that change in acoustic impedance is real. But what happened, for example, at around 2,150 meters, where my acoustic impedance is showing this increase, which yes, I do have it in the VP log, but my VS and my density are not showing the same behavior. And also, I don't have anything in the lithology track indicating there is a sudden change of lithology that could explain the behavior in the VP. So in this case, the log that is conditioned is the VP in this particular section, okay? Now, let's assume that the logs are fine, that you say, I really don't have time to do any QC or proper conditioning, so I'm going to work with my data as it is. So let's take a look at a synthetic gather. So I'm going to add a track. I already calculated one with our raw data. And let me please quickly change the displays. And let's reset the zoom. Okay. Now, let's start from the top. We can observe large amplitude anomalies in the shallow section, indicating subtle amplitude increases with angle, okay? And as you can see, every time, as expected, we have a sudden change on acoustic impedance, we have these high amplitude events, okay? So we have in the shallow section, we also have in deeper sections, okay? And again, zoom in for better looking. So for example, we have this peak at around 2,275 meters. And also we have this peak where we know that BP needs correction, okay? So if, for example, if you use this synthetic gather as it is to do a well type, this high amplitude event is going to be misleading, okay? Same if you would like to use it to estimate any wave. Now, if we take a look at the hydrocarbon section, this one here, my synthetic gather is not telling much. I don't see any significant AVO response, okay? And this could be real, but what if it's not? What if it's related to poor quality data, okay? So now, let's take a look at this well, but in a little bit more detail using the cross plot. So I already have some here open. So here we have the VPVS on the left-hand side and the VP density on the right-hand side, and I'm going to display the well. Now, in my density VP, I would like to add some rock physics templates, okay? So why am I doing this? Even though these rock physics models are not calibrated yet to my measured data, I can use them to start a rough QC. Because even though I'm not expecting my data to plot right on top of following the same rock physics model line, I'm expecting the data to plot with a similar trend. It could be parallel, it could be a cluster above or below, but a similar trend overall, okay? I'm also displaying acoustic impedance constant lines. And the reason I'm doing this is because these lines help to assess geological units in terms of acoustic impedance contrast. For instance, compaction and cementation. So we can tell a little bit of that by adding these acoustic impedance lines. On the VPVS cross plot, I have a few rock physics models as well, like Greenberg Castagna for clean sand, from clean shale, from limestone, and also in dotted or dashed black lines have constant line of velocity ratio or VPVS. So the first thing that we can see in both cross plot is for low values of VP, you know, on the left-hand side, I can observe some constant values of VP while my density and the VS is changing, is showing some variabilities. But the VP looks completely constant, and this is happening in the shallower section. So this indicates that I do need to condition the VP at least at the top of my well. Okay. In this case, I'm coloring my data by volume, by volume in this case visual, but you can actually color your data by formations or working intervals, as we name it in the software, because you need to make sure that the data is consistent within the same formation. Okay. Obviously, if you have a change of lithology within the formation, you're going to see some changes, but the changes should be real or make sense. Okay. So for example, let's go back to the density VP. According to my volume of visual, which is the one that I have here, points with a color by dark red indicates clean shell, okay? So for example, I have a cluster in here that I hope you can see that I'm highlighting with the mouse, showing that apparently they are clean shell, but something that caught my attention is that this cluster of data has VP value between 2.5 and 3 kilometers per second at very low values. So if I really want to know where these points are plotting, what we can do, we can actually add a polygon around them. Okay. And then we can come to our well, yes, we can do it in here. And it's highlighting that all these points correspond to the section where the caliper is indicating washout, meaning that we cannot trust these points, okay? We need to remove those and then model them correctly. And we know that the issue actually is in the density and not the VP, okay? So I'm going to remove. Perfect. Now let's bring back the VSVP. Again, yes, we already know there are some issues with the VP log in the shallow section of the well, but also there are some issues with the VS log. How do I know it's a VS log? I have points that are on the right-hand side of the VSVP cross plot. They have quite high values of VP, between 3 and 5 kilometers per second, but the values of VS are lower than 1.2 kilometers per second. I'm not expecting that kind of behavior. Actually, this point should be plotting right here with a VPVS of around 2. And also, VPVS, this point has quite high values, 4, 5, and even higher than 5. So this is a red flag for me to tell you that the VS needs to be conditional, okay, at least for this point. So again, we have to remove them, and then we can model them later on, right? So this is like a first pass, a single well QC. Now, when we would like to do a multi-well analysis, either to keep QC in the logs, to make sure that the logs from these wells plot with the same trend as well data that we have outside. It could be offset well data or well from the same study. We have to be aware of large changes in pressure regimes between wells, because if this happens, you have to treat these wells separately. So for example, if I would like to use 2 more wells to model VS, but I have overpressure in those 2 wells, but I do not have overpressure in this one, I cannot use those 2 wells, okay? Or I can only use the anomaly pressure part of the wells, okay? So be aware of that. Also, we need to look for large changes in temperature, okay? And changes in the positional styles over a large geographical regions. And of course, if you're working with deviated wells, we need to look for anisotropy, okay? And try to correct the logs before using them in any other, in the subsequent steps of the workflow. So, okay. So now I'm going to show you the multi-well QC that we normally do using the cross plot, because I want to use those to model the VS and the density, okay? So I'm going to minimize this cross plot and let's open our multi-well one. Again, we're in the same domains, the VS, VP, and density VP, okay? So here, I have the multi-well QC cross plot. I'm not including the well that I would like to conditioning. This one here is not yet displayed in this cross plot, okay? There is a reason why, I will tell you in a second. In the density VP cross plot, the first thing that we can observe is like at around 2.1 grams per cc, we have constant values of density but changes in the VP. So I don't know if you can see the blue triangle here. This is saying there's something going on, because if my VP varies, I'm expecting the density to change as well. So this is an issue in this well that we have with the density. The same well, I noticed, is also having some sample issues. And this is a great example to talk about sample issues. How do I know? Because when one of the logs has a different sample rate than the other, the points or the data behave like a worm light, like this. So this indicates that one of these logs have to be resampled, okay? But apart from this, overall, the data doesn't look bad. In the VSVP, we have some weird clusters. For example, in this well that I'm indicating with the mouse in light green, it plots with like a light or like a ball. So probably we will need to condition this well as well, and we cannot use them in the multi-well analysis to predict other logs. Now, in the VSVP, I'm going to break the well that we like to condition, okay? And something that I hope you guys can see is that this well is quite problematic because it doesn't follow the same trend as the other wells. This well is the only one showing incredibly high values of velocity ratio, and it's the only well so far that is showing that constant VP with changes in VS, okay? So this is an anomalous or problematic well, meaning that we need to do quite significant conditioning to it. And let's take a look at the density VP. I'm adding the well. And as you can see, again, the data from this well is not plotting following the same trend. But why? It's because of the washouts. These cluster of red points, they are outside the general trend. These are where we have the clean shells, but we have the washouts, so the density is very low. And again, here is because we have those issues in the shallow section in the VP log, okay? So again, I'm going to remove that well. So something that I was mentioning before, if you need to condition a missing logs or repair measured data, one option that you have is to use offset well data, okay? And for this, we always have to look for rock properties and relationships. For example, if you need to condition a VP, you can do it as a function of porosity or even as a function of depth. And also, if you have overpressure, you can condition a VP as a function of effective stress. But if you would like to condition a VS and density, you can use the relationship that they have with the VP. Or you can also use petrophysical information. So you can do, for example, V-shell, porosity, saturation, together with a calibrated rock physics models to predict the VVS and density. And then you can use these synthetic logs to repair the measured data. In this opportunity, I'm going to use these offset wells to repair the VS and the density log. And the way to do it is for the VS and VP to calibrate some Greenberg-Castagna constants, and for the density VP is to calibrate some Gardner constants, okay? So I'm going to start first doing the exercise for the VS VP, and then I'm going to move on to the density VP, okay? So I'm going to bring this to the middle. When we are calibrating Greenberg-Castagna constant, we have to have in mind that this equation, this empirical equation, only works for brine-berry sands, okay? And in this case, I'm displaying in situ data. So if you don't have enough data to do fluid substitution to brine, something that you can do is to apply a saturation cutoff, okay? So you can say only display data where my saturation is equal to 1, and then you can use this point to calibrate your values, okay? So what I'm going to do, I'm going to make sure that I'm using my brine-berry logs, okay? And as you can see, before I was mentioning that we had like a weird cluster of data coloring green. This data was corrected before doing a fluid substitution to brine, okay? So this is my data, brine-berry. And now what I'm going to do, I'm going to apply a cutoff of V-shell higher than 90% to make sure that I'm only using clean shells. Why? Because we need to do this calibration to end-member lithologies. A clear shell, a clean sand, limestone, hydrant, etc. Okay? So now, if you want to be very strict with the data that you're using to calibrate your Greenberg-Castagna constant, you can add a polygon to avoid including this scattered data. And that's exactly what I'm going to do. So I'm going to quickly, oops, sorry about the clicking. And now I'm going to add a best fit line. Okay, so now it's displaying the line, which is this one here. And I'm going to add the questions. You guys can take a look at it, but also I would like to save this as Greenberg-Castagna clean shell. I'm saving this as a rock physics model. And we need to repeat the process for the sands. So I'm going to change the cutoff, and in this case, it's going to be lower than 0.2. A comment quickly here. Because I'm saying volume less than 0.2, in this case, my volume log is the V shell, that doesn't mean that there is clean sand, okay? Because it means that it's just no shell. But if you have different lithologies like coal and hydride, limestone, and sand, make sure that you're using the right volume log, okay? In this case, because I know mainly I have a sand and shell, it's okay. So now I'm going to do the same. I'm going to add a polygon, okay? And I'm going to add a best fit line, the same one. Remember, you need to do this for each of the formations separately if they don't follow the same trend. In this case, because I'm lucky enough that my data followed exactly the same trend, I can get away with using the same trend for sands and shale for all the different formations. But if that's not your case, you will have to repeat this exercise for each of the formations individually. And then again, I'm going to save this as my Greenberg Castaña, but in this case, it's clean sand. All right, so now, let's move on to the density and VP. I need to do the same. I need to make sure that I'm using my brine bearing logs, okay? Because also, you can have a lot of bias if you use hydrocarbons, because the proportion of hydrocarbon changes from one well to another, okay? So it's easier to work with brine bearing logs, if possible, of course. Okay, so basically this cluster of data that we have here correspond to all my data brine bearing. And these lines that we can observe in here, they correspond to data that was already modeled, okay? So I'm going to apply a cutoff, but I'm going to start first with the sands in this case. I'm using the same cutoff as the VSVP for consistency. So now, what I'm going to do, I'm going to add a polygon to cluster the data that I would like to use to calibrate my Gardner sandstone line. So quickly, I'll do this. And then I'm going to add, in this case, instead of a linear regression, it's going to be a power law because the Gardner relationships are power law, okay? Perfect, so is this line that we can see here. We can display the equation if you would like, but actually, I would like to save this as my Gardner shell. Sorry, it's Gardner sand. Sorry about that. It's the sand. And then we will need to repeat the process for the shells. So now, what I'm going to do, I'm going back to my well, and I'm going to show you how we can use this different relationship that we just calibrated to the measured data to predict density and also to predict ABS. So I'm going to well ops, log prediction, and then first density. And here, I don't know if you can observe in pink, I'm already using a conditional VP that I did before the presentation. And we have different methods in RokDoc to predict density, but in this case, I'm going to use the icon sign method because it's a multimineral one. In any constant is where you're actually going to enter the scalar and the exponent, remember velocities in kilometers per second, important, for the different lithologies that you have. I already did this, so these values are correct. And also we need to enter a volume set or information about the lithology because we need to know where do we have kind of what lithology. And then we click on calculate. And now in red, in my density track, I have my new density, okay, calculated as a function of VP. Something that is important here, this red log, this density log is going to be used to repair the measured data, okay, the one in gray, not to substitute it. So where we know the measured data is real, we are going to use the measured data, and we're only going to use the new synthetic density where the caliper is indicating washout and where QC indicated there was some issues with the data. Okay, so now I'm going to show you how you can predict ABS. Again, from BP input condition. Normally, people use Greenberg Castaña to predict VS from BP, which is fine. That's why we did the whole exercise in the cross plot to calibrate the constants. But Greenberg Castaña is not valid when you have hydrocarbons, okay? So if that is the case, you need to use the modified Gassman option, which requires a little bit more information. So we need to have our conditioning density. This is why I condition the density first. And then we need to give some information about fluids, porosities, and mineral properties, okay? And in any constant is where we're going to enter the values of from our calibration. I already did this, so I know these values are correct. And then where it says default methods, we need to select a method to predict PS when the fluid substitution cannot be done. Okay, so basically where we don't have many sands, it needs another method to predict PS, okay? So while it calculates, I'm going to explain you how this works. So basically what it's doing is using the Gassman equation to remove the hydrocarbon from the BP, and it's inputting brine or water. And then it's using Greenberg-Castagna to predict VS from the brine-bearing BP log. And then again, it's using the Gassman equation to put back the in situ fluid of the hydrocarbons, okay? And as you can see here, now my log in red in the BP track is my new synthetic VS log that I'm going to use to repair my measured VS log, okay? And of course, I already did this. So I'm going to show you the new condition logs that I have here in black. So see the difference. We remove these weird spikes in the BP log that they were affecting the acoustic impedance. We make sure that the VS and the top and at the base make sense, so we are no longer have negative values on the Poisson ratio. And actually, I'm going to bring the Poisson ratio as well. Okay, so you can see the difference before and after conditioning. And also, let's bring the acoustic impedance so we no longer have so many spikes in the log. Now, let's take a look at the synthetic gather after conditioning. So I'm going to clone this track, and then I'm going to add a new conditioning gather and see the difference. We no longer have this blooming of amplitude that we have here in the shallow section. We do have quite high amplitudes, but not as high amplitude as we have before conditioning. We no longer have these high amplitude events, okay, where we have that sudden increase of acoustic impedance, same in the deeper section. And now in my hydrocarbon section, we start seeing a little bit of an AVO response. There is a slight increase of acoustic of amplitude with offset, which is the same response that I can observe in other wells, okay? So now, this synthetic gather is more robust and is better for seismic interpretation. And also, it will improve the well ties, the estimation of any deterministic wavelet, which at the end will improve the reservoir characterization. I hope you guys follow the workflow, and I'm going to now back to the presentation to draw some conclusions. Okay, so conditioning log data and a detailed understanding of how this data relate to pressure, temperature, offset wells, and regional trends is really the main objective of the particular part of the QA workflow. We need to apply a systematic approach to the editing and conditioning of the data and use local and regional models. And be careful if you would like to apply any kriging or any other statistical techniques that they have a lot of underlying assumptions. Make sure that you spend time and effort to understand how those models should be constructed and incorporate seismic data when you can. Watch out for uplifts and exhumation and overcompaction, and of course, also watch out for undercompaction, for overpressure, and any other mineralogical diagenetic effect that can have an impact on your velocity. Keep in mind also that there may have some type of rock that you're not considering in your analysis, but probably they have a significant effect in the modeling of the logs. So to conclude, the whole point is to always have a full set of conditional elastic logs that they truly represent the geology, okay, that you study, and then you can use these conditional elastic logs for any subsequent workflows. It could be to do a rock physics analysis, an inversion feasibility study, or even to use them for a model-based inversion. Well, I hope you guys enjoy this presentation. Thank you very much for your attention.